Hello. This is video 22. And this is all about an example BST or a BST example. And we're going to insert these in order. Now, not necessarily alphabetical order, but in the order that I'm going to list them here. Insert in, well, I don't even want to call it that then. You know what? I'll just leave it at insert. And I'll take them in order left to right. Hunter. These are strings, by the way. Christina. Drew. Dan. Matt. Natalie. What else we got? Alex. I'm going to underline insert so it doesn't look like one of the strings. Joey. Lottie. Ryan. And Matt. The end. And to make it look more like a tree, let me see if I can find a green that will actually write. This dark green has been a friend of mine. We'll see. We've got a root all by itself. Now I'm going to draw this real quick and then erase it. Here's the root. And there is our empty binary search tree. Our empty binary search tree consists of one external node and no more. Okay, so when I first insert something here, see, here's what I told you, I was going to have to erase it. When I insert something, that does become the root of the whole tree. Hunter. And since a binary tree has the possibility of, a binary search tree node, has the possibility of having two kids left and right, then we will need 2 pointers, count them 2, coming out of each one of our tree nodes, not just one. Linked list, that one-way trip, it was always pointing forward to the next, always the next, always the next. Here, we could split up. We could either go to the left or to the right. Oh no, how are we going to know? Let's see. Oh, another thing I'm going to do, and smear green all over my hand, until the very end, I'm not going to fill in all the external nodes. Since this one has data and it's going to have kids, I'm going to have internal nodes, so I'm not going to draw and then erase and draw and erase, but I'll do this just this one time for your benefit, and I'm not going to do it again. There are external nodes here. I'm just not going to, that's what I'm not going to draw and erase. I'm not going to fill in the external nodes until I'm all done. So these, back in the old pictures of trees, I would have had circles, but since we're headed toward actually thinking about implementation, I'm going to go ahead and draw these as if that's a node structure with what in it? Let me see, what's it going to need? A data field, and then 2 pointers to the next node. A left pointer and a right pointer for the left and right children. There's not officially a next pointer. Okay. Goodbye, external nodes. See you later. And here we go. Check off Hunter. Christina, here we go. We always start at the root when we're trying to find out where the next data value goes in the tree. So how do I decide? Christina, I'm looking at these as strings, so it's alphabetical, and it only has to look at the first letter. C is less than H, so Christina becomes the left child of Hunter. There. You see what happened there? And of course, Christina has 2 external nodes. I'm not going to draw them and erase them. They might be replaced. But since Christina is alphabetically less than Hunter, then Christina becomes Hunter's left child. Okay? We got this figured out already, don't we? Let's try Drew. Capital D. Until we have to use multiple letters, we could just use the first letter. D is less than H. Yes. But D is greater than C. Ruh-roh. So we've got to come back to the right. And I'm not labeling these, and I won't for every single one of them, but all of these are the left pointer and the right pointer to the 2 children. So Drew goes to the right of Christina in a node of her own, like so. Check. How about Dan? Well, start with a D. D is less than H, come this direction. D is greater than C, go that direction. Now D is equal to D, so I got to look at the second letter. So DA will make Dan the left child of node Drew. And it was just an unfortunate coincidence that at the moment we're just kind of zigzagging back and forth. That is not in general going to be the pattern. Let's see what happens here. Mat. M is greater than H. There we go already. H-I-J-K-L-M-N-O-P. Yeah. M is greater than H, so I'm going to put mat over here. So we've got some growing space for other branches of the tree. And mat becomes Hunter's right child. Check. Next is Natalie. Natalie, N is greater than H. N is greater than M. So Natalie becomes Matt's right child. With room for 2 kids of her own. Check. Alex, A is less than H. A is less than Christina. So Alex would come over here and be Christina's left child. Joey, H-I-J, yes, J is greater than H. Let me double check. H-I-J-K? Yeah, J goes to the right. J is less than M, so J comes back to the left and becomes Matt's left child. Check. Almost there. Lottie starts with an L, H-I-J-K-L. So it's greater than H, element less than M, H-I-J-K-L, greater than J, so Lottie becomes Joey's right child. Yikes, I'm running out of room over here. I didn't plan ahead. I should have scooted the tree back over here, but it's too late now. Lottie is Joey's right child, is that right? H-I-J-K-L, yes. Ryan is greater than Hunter because R is greater than H, R is greater than M, R is greater than N. So Ryan, even though there's not a whole lot of room, becomes the right child of Natalie down here. That says Ryan. It's hard to read. You're just going to have to take my word for it. That says Ryan. Check. Matt. M is greater than H. M equals M, so we had to go to the next letter, equals A, row, equals T. Sorry, Matt. You're already there. Can't insert Matt twice. No duplicates allowed. Okie doke. And there you have it. Now, think deep thoughts about that. I'm going to go ahead and erase the board rather than have a bunch of choppy little short videos. I'm going to erase the board and have some observations about what just happened here and see whether or not we can generalize. Man, these unstinky markers are hard to erase. I don't even know if they make the stinky markers anymore. I wish they did. They erase so much better and the colors were so much brighter. And the smell didn't bother me at all. I don't have any sense of smell. Observations. OBSV. Observation bullet point number 1. You can look back at the example and refer back to it and nod knowingly. The first node inserted in the tree, or inserted into the BST, to be more specific, is permanently, P-E-R-M-A-N-E-N-T-L-Y, permanently the root of the whole tree. If you noticed, since Hunter, I believe it was the first one inserted in the tree, that became the root of the tree, and no other node ever unseeded it. Hunter was the root of the whole tree throughout the entire lifetime of the tree, and it would continue to be that way. First come, first serve. Bullet point number 2. Each new node inserted in the tree. Oh, darn it. I forgot to go back and put all the little squares across the bottom. You can do that. All the unused left and right child pointers should be pointing at one of those little squares representing an external node. This note is what reminded me of that. Each new node in the tree replaces some external node at the bottom of the tree. And since I messed up and didn't do that on my diagram, I'll do a little fig to go with this. Fig B4, and I'll call this, I don't know if it matters, node M. With left and right children. And we don't care what the left is, but the right, let's say that's definitely an external node, and M is somebody's child. This is just a zoom in on one particular node of the tree. And maybe the N, let's insert N. If we insert N, then the new node, the new internal node that contains N is going to replace that external node that's to the right. So the after picture in this very limited example would look like M is still there. L is still whatever it is. Maybe it's internal, maybe it's external, who knows, who cares. But M is still here, and when I insert N, it becomes not only an internal node in its own right, but it swings off two external kids of its own. So here's what happened. Each new node, this new node that contains N, it replaced an external node and then in effect added two new external nodes to the tree. So you get rid of one and you get two more. Okay? And I used up so much space with that picture. I don't know that I've got room for the rest of my bullet points. I'll give it a shot. 3 searches. That's what we're here for, isn't it? That's what got all this ball rolling here. Searches in the average and best case are, wait for it, order log n. Every time we move to the left, we in effect on average are going to cut off half of the nodes of the tree that we're not even going to pay any attention to anymore. Whatever we're looking for, if it's say to the left of the root of the whole tree, then we will never look at the right of the whole tree. Every time we take another step down the tree, on average, we're cutting in half how many more nodes of the tree we're going to have to look at to find what we're looking for. That's what makes it log base 2 of n. Remember, this is shorthand for log base 2 of n. Searches in the average and best case are order log n and for dramatic effect rather than order n. What was order n? Well, order n is searches in our ordered list, the linked list. You got to look through everything before it to get to the one you're looking for. You don't go left and right. So this is when you're trying to figure out the price of a baker's rack, for example, and you're using a pretty bad strategy. That's an order n algorithm. We like to order log n that cuts in half the number of possibilities at each step you take. You know what? We're going to have to deal with my bullet point 4, which won't fit on the board. We'll have to deal with that later, so I'll just read these off, and these will show up in future videos when we need them. 4, my bullet point says, what good are the traversals? And I think I mentioned this in a previous video, so I'm just going to mention it over and over again until we actually need it. Pre-order. The pre-order traversal, let's see, that visits a node and then goes to the left, and then visits the node and goes to the left. It turns out that the pre-order traversal is what we'll need to use when we need to reconstruct the tree, the structure of the tree. When might we need to do that? An overloaded assignment operator. An overloaded assignment operator for a binary search tree is going to be based on the pre-order traversal. You can try it out yourself and see. If you go through and make visit insert in my clone, let's say instead of visit printing out the data to the screen, it actually takes the node where it is and inserts that to the clone binary search tree. If you do that in pre-order, pre-traversal order, pre-order traversal order, it's going to create an exact duplicate of your tree. Unlike the in order is actually kind of strangely the outlier. That's the most natural one. If you do an in order traversal and you constructed your binary search tree correctly, it's going to print out the data values, all of them in order, in alphabetical order. In our tree, it would start with, I believe it would start with Alex and end with Ryan, first to last. And you might think, well, why don't I use that for the overloaded assignment operator? If you do that and insert Alex first and whoever was second, and so on down the line, then your tree is not a binary search tree that's useful anymore. It's a straight line. The way it's described is it degenerates into a singly linked list. It would be nothing but go to the right, go to the right, go to the right, go to the right, which means we might as well just have an ordered list instead of a binary search tree. So the pre-order is actually the least useful of the three traversals. What good is post order? And I mentioned this before, post order is what we'll need when we do a destructor for a binary search tree. Until we get rid of the nodes down below a node, until those are deleted, it's not going to be safe to delete the node where we are. So until we deleted the nodes below n, it's no good to delete n. We're going to have a memory leak. Until we delete the nodes below m, we can't delete m, and so on. So that's just kind of a taste of how we'll be using those traversals. And aren't you glad I didn't write all that on the board? I will when we actually need it, when we call it up from the ranks and say, you know what, you're going to have to be part of my code now. But this will be enough for now. I'll see you online.